Welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we had seen an example of a WiMAX fixed profile WiMAX 4G communication system. We said the fixed profile of WiMAX has n equals to 56 subcarriers and the bandwidth per subcarrier is B by n, which is 15.625 kilohertz. That we saw is much less than the coherence bandwidth, which is roughly around 300 kilohertz. All right. Thereby, it converts, as we said, typical of OFDM, it converts a broadband, wideband communication channel into a set of parallel narrow band flat fading channels. We also saw from the specs that the symbol time, the useful symbol time without cyclic prefix is 64 microseconds in this OFDM, in this WiMAX communication system, and plus the total symbol time, that is OFDM symbol time, that is the information symbols plus 12.5% cyclic prefix gives rise to 64 plus 8, that is 72 microseconds, that is the total OFDM symbol time. And then we also subsequently later modified the system, OFDM system, to include a MIMO OFDM system, that is we modified this OFDM to MIMO OFDM to extend it to frequency selective MIMO communication system, that is to handle the problem of frequency selective MIMO communication systems. And we said is OFDM converts the frequency selective MIMO fading channel into a set of parallel flat fading MIMO channels. All right. And further we said that the output of such a frequency selective MIMO communication system can be modeled as a MIMO FIR filter, where the output Yk depends on not only x bar k, that is the transmit vector at current time, but also depends on x bar k minus 1, that is the previous transmit vector, x bar k minus 2, and so on, that is the inter transmit symbol vector interference now in this MIMO frequency selective channel. And we were starting to look at the architecture of a MIMO OFDM transceiver. We looked at the transmitter schematic. We said that we first, in a MIMO OFDM system, we have multiple transmit antennas and the IFFT operation has to be performed at each transmit antenna. Hence, we first demultiplex the symbols among each transmit antennas. Further, we demultiplex for the IFFT operation at each transmit antenna, serialize them, add the cyclic prefix at each transmit antenna, and then transmit them over the transmit antennas. And we had started looking at the corresponding receiver schematic. We said at each receiver repeat the same thing. I remove the cyclic prefix, parallelize it, compute the endpoint FFT, and now across each subcarrier I need to perform a MIMO detection. So, let me complete this module over here. Again, for the second subcarrier, I take the output from the second subcarrier at every output from the second subcarrier at every receive antenna. This is another MIMO, this is another MIMO detection block. I take the output and this again is all right. So, what I am doing here is I am essentially taking the output, from the second subcarrier at every receive antenna, and I am performing a MIMO detection. This is MIMO detection for the second subcarrier. In fact, here this has to be first subcarrier, and this is MIMO detection for second subcarrier, and so on and so forth. I do MIMO detection for all the n sub for all the n subcarriers as follows. For instance, one can now do MIMO detection. I compute the last and this is the MIMO detection for the last subcarrier. And further, after this module, I am going to convert this into a serial. I am going to serialize this. So, this is a parallel to serial module, this is another parallel to serial module, this is another parallel to serial module, and once I have serialized this at each across each subcarrier, what I am going to do is I am then going to again further do this across all the subcarriers, convert them from parallel to serial across all subcarriers. That is, once this has to be serialized, that is, you have a block for all the transmit antennas, you convert that into serial at each subcarrier, and then finally you take all these streams from these different subcarriers and convert them into multiplex that into one complete stream that can now be used as information by the higher layers or the applications. Okay. So, this is the complete MIMO schematic, MIMO receiver schematic, which essentially looks slightly complicated, but it is simple once you realize that the processing for OFDM has to be now done, that is the cyclic prefix removal and the FFT operations have to be done at each receive antenna. Once that is done at each receive antenna, you collect the information corresponding to each subcarrier at each receive antenna and do a MIMO processing, that is MIMO detection across each subcarrier, and once you do a MIMO detection across each subcarrier, you can again demultiplex or you can again multiplex all these streams into one large stream. So, this is in fact a multiplexing operation, all right. So, you can multiplex into one big stream. Okay. So, that essentially completes the transmitter receiver schematic of this MIMO OFDM system. As a result of this, one can convert the frequency selective MIMO channel, as we said already, into a set of parallel flat fading MIMO channels. Hence, let me write that down. Hence, employing MIMO OFDM, the MIMO frequency selective channel that is the frequency selective MIMO channel, the MIMO frequency selective channel can be converted into a set of parallel flat fading So, employing MIMO frequency MIMO OFDM, the MIMO frequency selective channel is converted into a set of parallel flat fading MIMO channels, all right. And now, how does the output look across each subcarrier? Across each subcarrier, we have a flat fading MIMO channel. So, if I look at the output across each subcarrier, I have y 0 equals h tilde 0 times x 0. In fact, these are now vectors. Y bar 1 equals h tilde 1 x bar 1, so on and so forth, and in fact we have y bar n minus 1 equals h tilde n minus 1 x tilde n minus 1. Now, you can look at it, this is a MIMO flat feeding MIMO channel across each sub carrier, that is y equals y 0 equals h 0 times x 0, y 1 equals h 1 times x 1. It is similar to OFDM, except that the y and x are now vectors, that is they correspond to vectors transmitted across all the transmit antennas, received across all the receive antennas, and the h's are in fact the sub, which are the sub carrier coefficients earlier, they are now flat feeding channel matrices corresponding to these different sub carriers. So, in fact we have, if you look at this equation here, if you look at a typical such equation, y bar k equals h tilde k into x bar k, we said this is the r cross 1 receive vector corresponding to subcarrier k, this x bar k is the r cross t cross 1 transmit vector corresponding to sub carrier k, and this h tilde k is now the flat feeding channel matrix corresponding to subcarrier k. So, h tilde k is the flat feeding channel matrix corresponding hence what we are saying is y equals h, y bar equals h tilde k times x k, y tilde k is the received symbol vector across subcarrier k, h tilde k is the transmit, is the channel flat feeding MIMO channel matrix, r times t dimensional flat feeding channel matrix across subcarrier k, and x bar k is the transmit symbol vector across subcarrier में, similar to cis OFDM. What this is the transmit symbol vector loaded onto the transmit antennas over the kth subcarrier. Alright, since this is MIMO, we have multiple transmit antennas as well as multiple receive antennas. So, essentially here we have, this is our set of, this is nothing but our set of n flat feeding MIMO channels. This is our n parallel flat feeding, this is our set of n parallel flat feeding MIMO channels. And now what we can see is each y bar 0 can be simply processed by the MIMO techniques that we had seen earlier, which was MIMO zero forcing receiver or MIMO MMSE receiver. Let us, just to complete that discussion, let us look at that. Each, what we are saying is each y 0, in fact y 0 bar, y 1 bar, so on up till y bar n minus 1 can be processed by a simple MIMO zero forcing receiver or a MIMO MMSE receiver for detection of the symbols, detection of vectors So, what we are saying is at the receiver, that is what we are doing in the MIMO detection, that is you take from each transmit antenna the information corresponding to subcarrier 1 and detect x bar 0 which has been transmitted on the 0th subcarrier. Similarly, you take for the kth subcarrier from each receive antenna you take the information received and form the vector y bar k, use the knowledge of h tilde k, that is the channel matrix corresponding to the kth subcarrier, and decode the transmit vector x bar k that has been loaded onto the transmit antennas across the kth subcarrier. That is essentially the intuition, and the MIMO zero forcing detection as well as MMSE are fairly simple. If you were to look at zero forcing, we say x hat k across the kth subcarrier is nothing but h tilde k pseudo inverse y bar of k, and this is nothing but, we said this is nothing but h tilde Hermitian k h tilde k inverse h tilde Hermitian k into this k is the kth subcarrier. Let me write this as j or L to denote the time across the kth subcarrier, h tilde Hermitian k into y bar of k. So, this is nothing but the pseudo inverse, and this is nothing but the MIMO zero forcing receiver. This is nothing but the MIMO zero forcing receiver. Similarly, one can employ the MIMO MMSE receiver, that is the MMSE receiver across the kth subcarrier, which is x hat k MMSE x hat k, the MMSE receiver is given as follows, that is nothing but PD, that is the data power PD h tilde Hermitian k h tilde k plus sigma n square identity inverse into h tilde Hermitian k into y bar of k. This is the MIMO, this is in fact the MIMO MMSE receiver. We are saying that the MIMO MMSE receiver is such that it estimates x hat MMSE of k equals PD, where PD, remember, is the data power. This is nothing but the power of the data on each transmit antenna, PD into PD h Hermitian k h tilde k plus sigma n squared I inverse times h tilde Hermitian k times y tilde k y bar k. This we said is the MIMO MMSE receiver. All right. So, this is the MIMO MMSE receiver. Employing this, we can detect the data across each subcarrier, and now once you detect the data across each subcarrier, you can take all the data across all the data on all the transmit antennas detected for all the transmit antennas across all the subcarriers and then multiplex them into one stream. Now, what remains is the detail of how to compute this flat fading channel coefficient matrices. So, if you look at these flat fading channel matrices H tilde 0, H tilde 1, H tilde n minus 1, how can they be computed? So, these are nothing but the flat fading channel matrices, these are nothing but the flat fading channel matrices these are nothing but the flat fading channel matrices across the flat fading channel matrices across the subcarriers, across the n subcarriers, and they are simply computed by the FFT of the channel taps, similar to what we did in OFDM, except now these are matrices. Hence, each element of the matrix is computed as the FFT of the corresponding element of the channel tap. So, to make it more specifically, let us look at the vector H tilde 0. I am going to look at the uvth element of all these matrices, that is u comma vth element of matrix H tilde 0, H tilde 1, so on, and the u comma vth element of matrix. If you take this n dimensional vector, this is nothing but the n point FFT of, this is the n point FFT of the uvth elements of the MIMO channel taps, which are H of uv comma 0, H of uv comma 1, so on and so forth, H of uv comma n minus 1 of comma L minus 1. Of course, this has to be taken after 0 padding. Since the number of subcarriers n is much larger than L, this n point FFT has to be computed after 0 padding. So, I take the uvth elements of all these channel taps, MIMO channel MIMO FIR channel taps. I compute the n point FFT, that gives me the uvth elements of the channel matrices across all the n subcarriers, all right, and then you do that for each element essentially of the MIMO FIR taps and construct the channel matrix across each subcarrier, all right. That gives the channel matrix across each subcarrier, and we can use this channel matrix similar and in the procedure that we have described before to either employ zero forcing MIMO detection or minimum mean squared error MIMO detection, and that completes the MIMO OFDM communication system. All right, so that completes in essence our discussion on MIMO OFDM. Now, I want to go into looking at some of the distorting effects on OFDM. What we looked at so far is mechanisms in which OFDM works, which is how OFDM converts a frequency selective fading channel limit, which is essentially introduces the distortion of intersymbol interference into a set of parallel flat fading channels to simplify complexity at the receiver. We also looked at MIMO OFDM, which converts a MIMO frequency selective channel into a set of parallel flat fading MIMO channels. Now, what I want to start looking at is I want to start looking at what are the kinds of problems that could arise in an OFDM system. For instance, the first one we are going to consider is the effect of a frequency offset at the receiver in the OFDM. That is, if you have when you have a carrier that is generated at the receiver and use that to demodulation, if the receiver carrier is matched to the transmit carrier, then we have no problems. But if the receiver carrier has a slight frequency offset, has a slight carrier frequency offset with respect to the transmitter carrier, then that can give rise to several problems, as we are going to look at in this section. So, what I want to start looking at is the effect of frequency offset in OFDM. So, what is the effect? What is the effect of frequency offset in OFDM? As we know, OFDM is based on frequency division multiple axis, that is, it is not the traditional frequency division multiple axis, but it divides the spectrum amongst a set of orthogonal carriers all right. So, OFDM is based on, so OFDM overlapping orthogonal carriers. So, OFDM divides the wide band, the available wide band amongst a set of orthogonal overlapping So, what OFDM does, as we have already seen, it divides the spectrum into smaller portions or narrow bands or smaller sub bands amongst subcarriers which are essentially orthogonal. So, these subcarriers are overlapping, yet they are orthogonal. That is essentially the beauty and the principle of OFDM. Hence, a carrier frequency offset, an offset in the carrier frequency can cause severe distortion in OFDM system. Hence, the presence of a carrier frequency offset can introduce severe distortion in an OFDM. This can introduce severe distortion in OFDM system, as it results in a loss of orthogonality amongst the subcarriers. All right. The problem with the carrier frequency offset, this OFDM system is a delicately balanced system, that it has overlapping orthogonal subcarriers. When you have the presence of a carrier frequency offset, what happens is, what essentially ends up happening is that the carrier frequency that this carrier frequency offset, it results in a loss of orthogonality of these OFDM subcarriers, thereby introducing interference amongst the subcarriers. Let us look at this pictorially. If you draw a picture of this, the subcarriers in an OFDM system, they look as follows. They look as sync pulses in the frequency domain. All right, I have one subcarrier here, and I have another subcarrier essentially adjacent to this subcarrier, which is exactly such that what I am showing here is, let us call this the Lth subcarrier in the OFDM system, and this subcarrier is the L plus 1th. This is the L plus 1th subcarrier. What you see here is that when I have a peak of the Lth subcarrier, that is when I sample the Lth subcarrier, the L plus 1th subcarrier is actually 0, and similarly when I am sampling the peak of the L plus 1th subcarrier, the Lth subcarrier is actually 0. So, this is essentially principle of orthogonality. This is essentially why the subcarriers are orthogonal. This is basically the principle of orthogonality of the subcarriers. Now, the moment I have a carrier frequency offset, I am offsetting the sampling time in frequency, which means I am offsetting slightly, I am sampling slightly off the peak. So, I am sampling at this point. So, this is the sampling new sampling point because of carrier frequency offset. This is the sampling point deviation because of frequency. This is the deviation because of the frequency offset, and as you can see now, when I sample this thing, the value of the desired subcarrier is lower, and more importantly there is interference from the adjacent subcarrier. This value here is nothing but this value here is nothing but the interference from the adjacent subcarrier, and this here, this distance here, this is nothing but the carrier frequency offset. This is in fact the carrier frequency offset. This arises because of the carrier frequency offset. So, as you can see, as long as I am sampling at the ideal frequency, that is the frequency that is matched to the peak of each of the subcarriers, I have no problem. But the moment I deviate from that because I have a carrier frequency offset, what is going to happen is there is going to be an interference from the adjacent subcarriers at each subcarrier, that is due to the loss of orthogonality amongst the subcarriers. In fact, this is known as inter-carrier interference, ICI, in OFDM communication system. So, let me mention that. Hence, presence of a carrier frequency offset introduces inter subcarrier inter-carrier interference in OFDM systems. Introduces what is known as inter carrier interference, ICI, in hence the presence of a carrier frequency offset introduces inter-carrier interference in OFDM systems. That is the problem, and once you have inter-carrier interference, there is no orthogonality and you have a big reduction in the SNR, and depending on the magnitude or depending on the extent of this carrier frequency offset, the larger the carrier frequency offset, the greater the inter-carrier interference and the higher is the reduction in SNR, or the lower is the effective SNR per subcarrier because of this loss of orthogonality amongst the subcarriers. So, what we want to do in this section is, we want to characterize the effect of frequency offset on the OFDM system. So, we desire to characterize the effect of frequency offset on the performance of the So, we want to start characterizing what is the impact of this frequency offset on the performance of the OFDM system. So, we start by considering a frequency offset such that So, consider a frequency offset delta f such that the frequency offset delta f is such that delta f by b over n, the subcarrier bandwidth equals epsilon. That is, this is the frequency offset, this is the subcarrier bandwidth. Hence, this is nothing but epsilon is nothing but the fraction of the frequency offset with respect to the subcarrier bandwidth. Delta f by b over n is nothing but the frequency offset as a fraction of the subcarrier bandwidth. Hence, this is nothing but this is the normalized frequency offset. This tells us what is the normalized offset as a function of the subcarrier bandwidth in this OFDM system. Now, given this frequency offset epsilon, it can be shown that the received samples y n at the OFDM receiver, the baseband received samples given offset epsilon, the baseband received samples are given as y n equals 1 over n summation k equals minus n by 2 to n by 2 x k h k e to the power j 2 pi n k plus epsilon by n plus w n. Hence, the received sample y n in the presence of a frequency offset epsilon, we are saying is given as 1 over n summation k equals minus n by 2 to n capital N by 2, where n is the number of subcarriers, x k h k e power j 2 pi n k plus epsilon divided by k plus epsilon over n plus w n. This is of course, this is the noise. So, this is nothing but this is the noise. Y n is the nth sample, this is the nth received sample, x k is the data transmitted on the, this is the data transmitted on the kth subcarrier, and h k is the channel coefficient across the kth subcarrier. And epsilon we said is the frequency offset. In fact, epsilon is the normalized frequency offset. Now, this is which is the nth received sample as a function of the normalized frequency offset. Now, to verify this equation, let us set epsilon equal to 0 and what happens. So, let us this is I have given some equation over here. What I want to show you is that I want to set epsilon equal to 0 in this equation, and I want to show you that it reduces to the same OFDM system that we had previously. So, to verify the above equation, set epsilon equals 0, what we obtain is y n equals 1 over n summation k equals minus capital N by 2 to capital N by 2 x k h k e to the power of minus j 2 pi n k over n plus w n, where w n is the noise. Now, when I perform the FFT of this, that is I receive all these samples y n, which is y 0, y 1 up to y n minus 1, and then we perform an FFT at the receiver, that is standard OFDM processing. So, performing an FFT at the receiver, the nth FFT coefficient corresponding to y l, which is the received symbol at the nth subcarrier, is given as. So, we perform the FFT of y 0, y 1, y n minus 1 at the receiver, that is at the receiver we collect y 0, y 1, y n minus 1, and we perform the FFT of these symbols at the receiver. And y l, now after performing the FFT, consider the nth FFT coefficient which corresponds to I l. Consider y l, consider the nth FFT coefficient capital Y L, which corresponds to data received on the nth subcarrier, which corresponds to the symbol received on the nth subcarrier, which corresponds to the symbol received on the nth subcarrier. This is given as y of L equals 1 over n summation y n e to the power of minus j 2 pi n L over n. This is nothing but the simple nth FFT coefficient, that is y L, capital Y L equals summation 1 over n summation y n e power minus j 2 pi n L over n, that is I am computing the FFT coefficient, and this y L it can be shown to be equal to y L equals 1 over n summation n. I am substituting now the expression for the y n that we have, which is k equals minus n by 2 to minus n by 2 x k h k e power j 2 pi n k divided by n e power minus j 2 pi n L divided by n plus w tilde of L. This is equal to 1 over n summation k summation n. I am going to combine this e power j 2 pi k over n, e power minus j 2 pi n L over n as x k h k e power j 2 pi k minus L n over n plus w tilde of L, where w tilde of L is nothing but the FFT coefficient, nth FFT coefficient of all the noise samples. This is also a noise sample, w tilde L is nothing but the FFT coefficient of all the noise samples w 0, w 1, w n minus 1. And this is nothing but, now when k equals L, in that case this is 0, the summation over n is n, n over n is 1. So, this reduces to XL HL plus summation over n summation over k equals minus capital N by 2 to capital N by 2, k naught equals L, that is we have extracted the term corresponding to k equals L over here. So, all that remains are terms k naught equals L, xk hk e power j 2 pi n k minus L over n plus w tilde of L, and we see that when k is not equal to L, this summation, that is e power j 2 pi n k minus L over n summed over n, this summation equals 0. So, this summation over n, in fact when k is not equal to L, this summation e power j 2 pi n k minus L over n, this is in fact equal to 0. Hence, what we can write is, in the absence of carrier frequency offset, we have Y L equals H L times X L plus W tilde L. So, in the absence of carrier frequency offset, remember, in the absence, this is in the absence of any offset in the carrier, in the absence of carrier frequency offset. This is in fact the original OFDM system. This is in fact the original OFDM relation for the Lth this is in fact the original OFDM relation for the Lth subcarrier that we have in this system, that is YL equals HL times XL plus W tilde L, that is across each carrier the channel is flat fading, that is YL equals the flat fading channel coefficient HL times XL, data transmitted on the Lth subcarrier, plus W tilde L, which is the noise. This is what we received in, this is of course, this is in the absence of any carrier frequency offset, that is here I have to add, that is epsilon equals 0. Remember, this is valid when essentially epsilon equals 0. Now, let us go back to our original expression in the presence of a non-zero carrier frequency offset. Now, consider, go back to the original expression. Now, consider the received symbols y n in the presence of a carrier frequency offset. We have y n equals 1 over n summation k equals minus n by 2 to n by 2 x k h k e to the power of j 2 pi k plus epsilon divided by e to the power of 2 pi k plus epsilon divided by n plus w n. There should be n over here. So, k equals minus n by 2 to n by 2, this is x k h k e to the power of j 2 pi k plus epsilon small n over capital N plus Wn. This is the original expression we had. Now, let us consider a DFT. What happens when we take an FFT of these received symbols with a carrier frequency offset at the receiver. Now, after DFT, at the receiver of these symbols with the carrier frequency offset, similar to what we did before, that is we want to compute YL, which is the received symbol across the Lth subcarrier. The Lth coefficient YL corresponding to symbol received on the Lth subcarrier is, we have again the same expression, which is YL equals 1 over n summation Yn e power minus j 2 pi NL over n, that is the Lth coefficient after the FFT. This is nothing but, this is can be simplified substituting Yn. Now, this can be simplified as, summation over n k equals minus n by 2 to n by 2 x k h k e to the power of j 2 pi n k minus L plus epsilon. Earlier, remember, we only had k minus L. Now, because of the frequency offset, we have this factor k minus L plus another factor epsilon divided by n plus, of course, the noise that we are also taking minus e power j pi 2 pi n L divided by n. Okay. And now, let us employ the similar simplification that we had employed earlier, that is, when k equals to L, this reduces to k minus L is 0, and this is simply e power j 2 pi n epsilon over n, and when k not equals L, there is some other expression. So, due to lack of time or the shortage of time, I am going to limit this discussion here, and we are going to start here and continue with this in the next lecture to look at what is the effect, what is the impact of this carrier frequency offset epsilon on the SNR across the Lth subcarrier. Thank you very much.